been tremendous amount of things going on in astronomy. And it started out with LIGO, which you'll get a copy of here in a little bit. And that was a large-legged interferometer they put in place. One of them is in Washington, the other one is down in the southeast part of the country. And they, for the first time, managed to see gravitational waves from two black holes colliding. And not just see it, but it was, they really had been working for years to try to get the signal high enough so they could see it because of the noise generally. And this came in extremely loud, and it came in while they were still testing the equipment. So they weren't sure whether it was an accident or what happened because there was so much signal. But the importance of detecting gravitational waves and being able to actually begin to measure amplitude and strength and where they originated is that it goes back to really proving Einstein's general theory of relativity that he put out in 1915. And of course, when he first put it out, everybody looked at it and it was like, this can't be real. This has got to be imagination, or as they said back then, Gedanken, which was basically a thought type of experiment. But over the years, basically in 1974 and then most recently in 2015, there's been a number of experiments that people have been able to do that not only see gravitational waves, but to get a much better understanding of what they are. And what they are, and it's really hard to imagine this, it's the fabric of space-time warping and wiggling, if you will. So way back when, Michelson tried to do an experiment to see whether or not there was an ether, what he called an ether, because the only way that light waves and the rest of these waves could propagate through space is there had to be some kind of a medium that they would propagate in. And his experiment turned out to be a total failure because there wasn't an ether per se. But now with a better understanding of what space-time is, it turns out there is kind of an ether, not what was originally thought, but there is a structure in the universe on which planets, galaxies, everything reside. And that structure is not stable. It's continually expanding right now because the universe is expanding, so the space-time fabric of space itself is expanding, and as a result, the planets and galaxies and everything are moving apart, except when they're close enough together where you get gravity. So the reason I gave you these handouts is that it explains a little bit about what these experiments are. It does talk about what gravitational waves are and how they measure them. But some of the more interesting things that have come up in astronomy recently were not only these gravitational waves, but because of the nature of being able to measure gravitational waves and to measure the centers of galaxies better, it's been discovered that every single galaxy has a supermassive black hole in the center. And these are huge. These are somewhere between 1 billion and in some cases as much as 1 trillion sun masses in a single black hole. So it's got everybody thinking right now, how in the world could any black hole get to be this big? In some cases, the black hole at the center of the galaxy contains more mass, way more mass than all the stars in the galaxy combined. And every galaxy out there now is seen to have one of these black holes in it. As they look further and further out in the universe, and they see every one of these galaxies having a black hole, they're looking back to the beginning of when everybody believes the Big Bang occurred or when the galaxy originally originated. And they're finding big black holes back as far as you want to go. And that's really mind-boggling because originally when they thought of the Big Black Bang, they thought it was this creative event that was going to create a distribution in the universe that was extremely homogeneous. No perturbations in it. When they looked, they originally began to see with some of the background, and the cosmic background is what is the leftover, if you will, from the flash of the Big Bang. It has redshifted down to the point where it's at microwave frequencies now, and then looked at these microwave radiation throughout the whole galaxy, and they found small perturbations. They found perturbations more than you'd expect from just a very homogeneous explosion. But now with a better understanding of gravitational waves, a better understanding of how gravity works, and a better understanding of black holes, a very interesting set of what they call Gedanken experiments are occurring. People are looking at this and saying, what if? And one of the big what ifs now, what if that original Big Bang flash we had was actually the collapse of a black hole in another universe? Because all of the things we see are indicative of that being the case. If you have, when you look at a black hole, when it begins to form, you have an event horizon around that black hole, and time and space itself is warped. If light goes close to a black hole, it's bent. The black hole acts just like a lens. And the reason it's acting like a lens is as that light passes through the outer regions of the black hole, the time slows down for that area around the black hole. The closer you get to a black hole, the more time slows down. As the light goes around, if the path of a light is two parallel rays slightly far apart, and the time is slightly slower on the inside, it's going to bend that beam, just like a lens. If you continue that experiment, and you say, okay, the further I get into a black hole, the more time slows down. What happens as you begin to approach the singularity itself, time asymptotically approaches zero. So if you could be in the center of that black hole and exist, which you can't, but if you could, and there is some way you could look out in the rest of the universe, your time is going so slow that the entire time in the rest of the universe would go by in a flash. Zero time. Because your time is so slow, time anywhere else then is much faster and faster and faster. So when the gravitational strength gets to be close to infinity, your time goes to infinitely slow, then everything coming in is infinitely fast. So if I could go back and look at the center of that black hole and say, well, space-time as we know it doesn't exist anymore there, then you're creating a new space-time fabric. And to the inside of that black hole, you'd see a flash where everything that that black hole acquired over its entire life would be come to that hole and come out in this new space-time fabric as a flash, another Big Bang, if you will. So it looks like, at least some of the thought experiments, that they have not been able to prove this. They'll probably never be able to prove it. But it's an interesting concept to look at the fact that as mass goes into a black hole, it doesn't all go in at the same time. It comes in over a period of time, over years, but over millions of years. But as you get to the center, as that time goes to zero and the rest of the time becomes a flash, there's still a very small change in that flash as far when it started to get bright, when it became totally bright, and when it began to get dim. That difference in intensity would be a function of when that mass fell in that black hole. So these are all conjectures at this point. But it's an interesting idea to look at where, as we begin to understand the nature of general relativity better, the nature of the universe better, the nature of all these things interact with each other, that all new kinds of ideas, we talked about parallel universes, they talked about all these things, and there's actually mechanisms now where it's becoming more and more straightforward to look at these things and understand them. So, are there any questions? Yes?
Who's the next Stephen Hawking?
Who?
Who is the next Stephen Hawking?
I don't know that there is one right now. There's two people at Lawrence Livermore that have done most of the work with understanding gravitational waves. Most of the stuff on these supermassive black holes is being done with Cambridge right now, and one of the laboratories in Hawaii. So we'll see who comes out of the mess as being one of the best. But there's a lot of people right now that have, I won't say they're as smart as Einstein because Einstein was unique, but there's a lot of people that are doing a lot of work right now. And it's an exciting time. If you're in physics and astronomy, I mean, it's goosebump time as far as what they're discovering. Yes?
Has Neil Tyson deGrasse done a YouTube on this subject?
trying to think of if one has been done. There's one that's been done on LIGO, which is the interferometer in Washington down, but the other stuff I'm talking about, this is just me talking with friends I know that stayed in physics when I went bad and went off in another area, so.
Interesting.
Tim?
Thank you.
Oh. Okay, I would have had more today, but as I said, yes.
I actually do have a question.
Yes.
So they found a black hole, correct, recently?
Well, they have taken a picture of a black hole. They found basically thousands of black holes. And what they've done is they've done enough work now to know that there's these supermassive black holes at the center of every one of the galaxies out there that they've been able to look at.
Are they concerned about any of those black holes causing another Big Bang? And if it does, what will it do to us?
Well, the interesting thing, as time goes to zero in the black hole, all the time in our space-time, from the beginning to the end, however long that is, will occur before those black holes go bang. And the reason is, I said that as you get into the black hole, time slows down. So it takes infinitely long in our space-time for the matter that comes to that black hole to get down to the center. It can't get to the center as long as we live, basically. Because by the time it gets there, infinite period of time it goes by, everything here is going to be cold and gone when those black holes start doing their thing. So what you end up with is space-time is relative. The space-time we have here is different than the space-time that you'd have out by Jupiter. And the reason is the gravitational fields are slightly different. A lot of things are slightly different because it's different than a measurement that we take here. If we go out there, the measurement will be the same because it'll be relative, will be there. But if I could look at a lot of measurements exactly here, and they're simultaneously, we see a small difference. The GPS satellites that are cycling up there have to have general relativity corrections to make them accurate enough to give the dimensions that we have here. And the reason is they are high enough up in the sky that the gravitational field there is slightly less than it is here, so time is slightly slower for us than it is for those satellites up there. And that makes a difference when trying to accurately determine places on the Earth.
So then can we trust our iPhones when they change time zones?
Probably. We're talking about, nanoseconds kind of differences. Yes?
So I'm understanding your description of gravity. Thought gravity was a force, and a lot of people have conjectured as in physics, for every force there's an opposing force.
Mm-hmm.
Okay, and what I'm understanding you to say is that it is not a force, it is a wave. It's a medium that a force can travel over. Is that correct?
Force is a way of measuring an attractive field between two different objects, right? And it can be plus or minus. Well, they haven't found a negative gravitational force. As close as we've come to finding a gravitational force, space-time itself is expanding. And the expansion of space-time, another way of talking about it is dark energy. And dark energy is causing the universe to expand. So if there's a anti-gravity, so to speak, it's the effect of this dark energy and the expansion of space-time itself. If that makes sense.
So it's not. So it still is a force, not a medium force.
Well, it's not a force. Normally, we look at forces and we see an exchange of two particles. So if you have a electrical force or magnetic force, in those two cases, there's photons, which are exchanged, virtual photons, it's called, and that's the mechanism of having force between things with electromagnetic energy. It's the way that photons have momentum when when a photon of light hits something, it actually imparts a momentum to it. If you've seen these little whirligigs that have the black side and the silver side, then those things will spin in a vacuum. And the reason is that the light coming in, the momentum transfers more to the silver side because it's reflected than it does to the black side where it's absorbed. And as a result, they'll spin just from the force of light. So there you've got actually photons or electromagnetic waves that cause the force. And you can just point to it and say, this is it. They looked for something called a graviton for a long time, which was a mythical, or at least imagined, force of gravity. And the net result was they went back to general relativity and said, it's not a force like we normally think of, but it's a warping of space-time that there's an apparent force. And it has to do with mass or energy, both of which have a gravitational effect on another thing. And the more mass you have, the more space-time is warped, and the more things bend or have what looks like the force of gravity. Yes?
Is your interest in astronomy more of a hobby, or is this an extension of your professional career?
I gave up physics as a profession back in 1978. So but I knew a lot of people, and I've maintained contacts with those people, so periodically we'll write to each other, or I'll talk on the phone to them, and it's been really interesting to keep my fingers in it. I would have liked to have been in that field, but I would have starved to death, so.
Right.
Yes.
Have you met the fellow in Nasika Beach that did that prevented the Fukushima radiation from coming on shore? Have you met him? He's an interesting guy.
He is, and I have just had it by verbal information from Carl King, who has met the man and who has made me detour the area. Can't prove it. Nobody's ever going to go through one. I mean, this is the ultimate wormhole, except that there's no returning. You can go into it, and you're totally dissolved into raw energy by the time you get to the center.
With these gravitational forces that they're understanding, and are they putting anything into like propulsion, to travel using these as mechanisms?
Well, since you're warping space-time, what you're talking about is having some way to effectively warp space-time. And right now, it takes a concentration of energy or matter to do that. So unless you can artificially create a bunch of matter or a bunch of energy and put it in a point and have it right out in front of you some way, but then it would have mass. So there's going to be conservation of energy. By the time you get done, you're not going to be able to accelerate, because how can you carry something with you that's your own acceleration? So you need an external force of some kind, and at least I can't think of anything that would do that. But it really, it's kind of interesting that they made all these movies with time travel and all this stuff, and most of the stuff is unwinding at this point. It's becoming so clear to how much fiction was built into the fiction. I mean, we'd always like to think that sometime we'll be able to have faster than light travel and the rest of that stuff. The reasons why it's never going to occur are becoming clearer and clearer, I guess.
Do you think someday we'll be able to travel through, man will be able to travel through hyperspace?
I really don't think so. It makes a good science fiction.
In the meantime, we can count on death, taxes, and gravity.
And gravity. It's looking more and more unlikely that, we're never going to explore space, that we're never going to, at least not as corporeal beings. Maybe an energy of some sort could, but we're not going to do it as human beings.
It's too bad.
Yes?
What's interesting is that this is the cooperation of competitive universities on opposite coasts of the country, Caltech and MIT, and it's funded by the National Science Foundation in part. It tells us the importance of having governmental financing for basic science research.
That's really interesting. I mean, yeah, it's a hobby for me, but this is the most exciting stuff I deal with personally, so. Any other questions? You've all got handouts. Up on the top, you've got I got most of this stuff from the Caltech site. So you can go to that Caltech site, and there's lots of videos, there's lots of Additional information you can see, you can actually hear two black holes colliding. It's very interesting to listen to it if you go to the website. So it basically, the sound that you hear is these two black holes getting closer and closer together until they merge. And for something as big as they are, it's an awfully high frequency of something that big moving that fast. Thank you.
Thank you.
Thank you.